Okay, so let's get started. So the idea today is to finish our discussion on non-separable perceptrons and talk a little bit about gradient descent as an optimization algorithm that we will use over and over again in this course. So please make sure that you understand this concept very clearly today, because in the future classes we will sort of build upon that, and that's kind of you could call this like a backbone of all machine learning algorithms, the general strategy that we are going to see today, right? So just to give you a little bit of recap, what we did on Friday was we took a step beyond what we had been looking in the first 2.5 weeks, which was first 2 weeks, right? Which was saying that, okay, in the beginning we thought that we are trying to learn a concept, right? And always remember that when we are talking about binary concept, it is a function that colors things in 2 colors or gives them 2 labels, right? So the first assumption we made was that, okay, we are going to assume there is some concept hypothesis space, and we are going to make a strict assumption that our target concept lies in that hypothesis space. But then we moved on and we said, what if this is not true, right? What if the concept that truly colored the data or labeled the data is not part of our hypothesis space? And the question that arises first is, then why do you go with that hypothesis space, right? The answer is that you want to come up with algorithms that you can actually implement, right? So that's why you keep a small hypothesis space or a simple hypothesis space and then learn there. So then we introduced this notion of the principle of good enough, which is that, okay, now since the target is no longer in the hypothesis space, that means you'll never be able to learn it, even if you search through that hypothesis space. So what can we do now? So the answer was that, can we learn a hypothesis which performs as close as possible to the target concept? So you might make some mistakes, but how can we learn a hypothesis which will make the least number of mistakes, right? So we are looking at this in the context of perceptron algorithm, but this applies to any machine learning algorithm, right? So you define some notion of performance, like the loss on your training data set or some sort of a likelihood, and then you optimize that objective function, and then you find the weight or the parameters of your algorithm, whatever they may be, which maximize or minimize that objective function, right? General strategy. So to do that, of course, we started talking about, okay, what are the ways to do this, right? So essentially you need to come up with some kind of an optimization approach, right? So for perceptron, we defined this as our loss function. So remember, this is an unthresholded perceptron, which means that it is only outputting the scalar value, which is taking the inputs, doing an inner product with your weight vector, which is W, and then it gives out an output, which is just a scalar value. When we use perceptron for testing, then we have another step, which is we do a thresholding if it's greater or less than 0, right? But here what we are saying is that let's compute our error like this, okay? And later today in the class, I'll talk about other ways to compute the error as well. But here is what our error is. So the problem is this: we are given some training data, which means that we are given some xi's and we are given some yi's. We want to find the weight vector which minimizes this loss function. So it is easy to pose this as an optimization problem, and I assume that you are familiar with numerical optimization, but just to sort of give you a brief recap, right? So let's talk about some basic stuff here. So let's say there is a function f of w, where w is just a scalar. So w is in the real space, right? So it could be 0.1, 0.3, so on. So let's say f of w is something like 2w square plus 3w plus 7, right? Now you want to find out the value of w such that this is maximized, let's say, right? So that is a constrained, or no, unconstrained maximization problem. You could also do something else, which is you want to find w which minimizes this. And then you could also have constraints, which is say, okay, you say I want to find w that maximizes this, but I also want to have w satisfy certain constraints. We will not look at that right now. Later we'll see some algorithms that do that as well. So how do you solve this, right? So one way in your math classes you must have seen, one way to do it is to compute the derivative. So you can write the derivative like this, f prime of w, which is nothing but d by dw of fw, right? And then you can compute this for this one. This will be 4w plus 3. And then the idea is that the first derivative will be 0 if you're at the optima positions, right? So if your function is whatever, right? So let's say, I don't know how to draw this function, but let's say your function looks like this. Then at this point, so this is f of w, this is w, the gradient will be 0. And then you can, if you can solve for this, then you get the answer, right? So you can set f prime of w equal to 0, and then you say w is equal to minus 3 by 4, right? So that gives you the optimal or the value at which the function is optimal. But in many cases you might not be able to set it to 0, right? You might be able to compute the derivative. So for example, f of w could be some insane 6 log w plus w e to the exp minus 2w square plus 8, right? So you can compute the derivative, sure, right? You can you know how to do that, but setting it to 0 might not be easy. So in that case, what you do is what we call the gradient descent method, and I'll talk to you about that. So before that, just to give you all a background on why this is true, right? Why is value gradient equal to 0 at minima or maxima? One way to look at it is to do what we call the Taylor expansion of a function, right? So if you look at the class notes for today, the handouts, you'll see a little discussion of that. So Taylor expansion, right? So Taylor expansion of a w around any point w naught can be written as f of w naught plus, I forgot, 1 over 1 factorial w minus w naught f, the first derivative, plus, I might be off by a little bit, but, and this is the second derivative, and so on, right? So there are many ways of these optimization methods. So the first order methods, what they do is they ignore this part, right? They just look at Taylor approximation like this, that f of w at any value is equal to a value close by. So as long as w naught is close to your w, you can write it like this, right? Approximate it like this. Now what you can see is that if w is a optimal point, right? Let's say w is a point at which f of w is minimum, which means that f of w minus f of w naught will always be less than 0, right? Because it's the minimum point. So this value will always be less than any point around it, right? Which means that if this condition need to hold and this value is always less than 0, then this should always be equal to 0, because we can choose any w naught, which means that we have no control on the sign of this. This can be less than or greater than, right? Because you are looking at any value w and you're trying to approximate it with a w naught here or w naught here. So w minus w naught can be positive or negative, right? So but if you want this to be always true, this minus this to be always true, then the only way that can happen for any w naught is that if this is equal to 0, right? If this is equal to 0 at w. And that is why we do this. So this is just sort of a background, really background stuff for all of this. But this will come up later, because later on we'll be doing higher order Taylor expansion. So we'll go to the second derivative as well and look at the second derivative, right? Any questions so far? Okay. So how do we do that, right? If we can compute the first derivative but we cannot set it to 0, one way to find the right answer is what is called the gradient descent algorithm, which is maybe the most basic numerical optimization algorithm, where what you do is you start with some w. So we said w is some value, right? So you can start anywhere here, and this is our w. Then you slowly sort of move towards the maximal point or minimal point. So this works in either case, right? Because if you're trying to maximize FW, you can always minimize minus FW, or maximize minus FW if you're trying to look for the minima. So that is not a problem at all. So the way this works is like this. So imagine that you are climbing Mount Everest, right? So you're climbing Mount Everest, and it's blinding snow, so you can't see anything. So, but you need to get to the peak, right? You can't see anything, snow in your eyes. All you have is the sense of touch, right? So what do you do, right? What you will do is, you just, because your eyes are closed, you're blind, right? So let's say you have a pickaxe. All you do is you tap, tap, tap around you and figure out which direction you see the, the most slope. And you basically take a step towards that. Then you again do the tap, tap, tap around, then take the next step until you reach a point at which everywhere you tap around, everywhere you're going down, right? Which means that you have arrived at the top. Fantastic, right? Your name goes into the papers, and you have not only scaled Mount Everest, but also understood gradient descent. So that is sort of the idea behind gradient descent as well. The only thing is that how does the algorithm do the tap, tap, tap around, right? The way it does is by computing the gradient at the point at which it is, okay? And because if you go back to your, calculus things, the gradient of a function tells you the direction or the slope, right? At the slope of the tangent at that point. So if you move towards the gradient, essentially what you would be doing is you would be moving towards the direction of the steepest ascent. That is the direction that the slope is going up the most. No other direction, right? So if you keep going up, you will be guaranteed to, it is guaranteed that you will reach the top, right? The same thing you can do in the other way. Let's say you're trying to get down and you reach the top. Now you have to get down back to the home base, right? So now you basically follow the negative direction of the, yes, go ahead.
What if your function looks like a double hump?
Right. So yes, so that's a very good question. The question is, what if the function is not like this, not just one peak, but it looks like this, right? And unfortunately, you started here, right? So these are what we call saddle points, or you can also call them local optima. So this is a point that if you are here and if you're not looking too far around, you might think this is the peak, right? But the actual peak is over here. So the point is that in that case, gradient descent won't take you up there. So gradient descent only guarantees convergence if your function looks like this. So mathematically, we call these convex functions. Convex functions are those such that if you take any 2 points on the function and you draw a line between them, they'll always be within the under the function, right? So that's the idea. So this won't be a convex function, because if I took these 2 lines, these 2 points, and connected them, they're outside, right? So that is sort of a notion of so if your objective function is nice and convex, and some objective functions are, but in reality they are not, right? If they are nice and convex, then it is fine, you will reach the top. But if it is not, then there is no guarantee that gradient descent will take you to the top, right? So the way, one simple way to handle it is, maybe you can do many runs. Every time you start from a different point, and maybe one point you'll be lucky, right? So basically you ask the helicopter to drop you at different points of Mount Everest, and every time you keep going, right? And every time you would reach some optima, and then you can compare which time you reach the highest, right? So maybe that's, but in general, gradient descent can only guarantee this if it is smooth, if it's convex, right? Another thing is that the function also needs to be continuous. There shouldn't be any point where the function is not defined, because that's where you fall into the deep ravine, and that's not good, right? So we always assume that function is always defined every point of x, of course. And another thing that we also want is the function should be smooth. All these functions, they don't like these kind of pointy ends. It hurts them, right? So it shouldn't be like this. That's no good. It should be smooth, right? Because at these points, on this side of this point, the derivative will be different. On this point, it will be different, because it's a sharp transition, right? So your gradient descent will not work in those scenarios. The only case where it works perfectly is this, and you can also apply it in this case with the additional grain of salt that you might not reach the maximum. Okay. Now I want to take it one step further and talk about functions which have more than one constraint, right? So what if your function looks like 4. What if your function is like this? It is a function of a vector w. Okay, so w, and let's say w has two entries, w1 and w2. So it looks like 7w1 plus 8w2 square plus 9w1 w2 plus 10. So we want to find, now here what we want to do is we want to find the values of w1 and w2 which maximize your function, right? So suddenly things have become a little more interesting, right? Now the first thing now the similar principle holds here as well. You need to compute the derivatives here too, but of course now we don't call it a derivative, right? So we call it partial derivatives. So you can compute the partial derivative of f of w with respect to w1, in which case you will consider w2 as a constant, and then you can compute the partial derivative of w with respect to w2, right? So typically what we do is we put this into a column vector and we call this the gradient of the function. Okay, so this is known as the gradient of a function. So if you have a function with d unknowns, right, then if you compute the gradient, it will be a d length vector, because you will compute the partial derivative with respect to each one of them, right? After that, the gradient descent is kind of similar. What you do is, oh, I didn't tell you the exact algorithm, right? Well, I'll get to that, but the idea here is again the same. So you compute the gradient instead of the derivative, right, because it's a function of many arguments, and then you move along that. So that gradient still sort of tells you. So let's say instead of just climbing a straight curve, you're trying to climb a mountain, then the idea is same, right? So now your function is a function of x and y, two arguments, or w1 and w2. So you compute the gradient which tells your direction in this 2D space, right? And then then I'll tell you what to do with that. Right. Now one thing you want to remember, just because this will come up later, is that if f is just a function of w, which is w is in just r, is a function of one value, then you compute the first derivative, and then sometimes you also compute the second derivative, right? This is essentially dy dw of f prime of w. In the case of vector, so if you're considering a function of a vector where f is, let's say, just for sake of example, it belongs to R2, that means there are two unknowns, then you compute what is called gradient, which is just a vector of the partial derivatives, and then the corresponding second order thing is what we call the Hessian. Okay, so this is a Hessian of the f, sometimes you just write h, this will actually be a matrix, because what you do now is you compute the partial derivative of each one of these things with respect to w1. So you'll first compute partial derivative of the partial derivative of this thing, then you compute the partial derivative with respect to w of this thing, and here as well, right? So this is known as the Hessian. So that's the second order derivative. So if you reach back to your old math books and you look at the Taylor expansion of a general function, not a function of just one value, but if you compute the Taylor expansion of a f of a vector w, then you will see, instead of this, you will see a Hessian there, and here you'll see a gradient, right? So that is the idea. This is just background which will come up later, so I thought I'll just talk about it today. Any questions so far? Okay, so now let's talk about the gradient descent algorithm, right? So the general idea, we understand that we start from some point, we compute our gradient, or we compute the gradient, right? That's true. So gradient descent, right? So start with w as some w naught. The initial choice doesn't matter. Well, it matters, but there's no principled way of finding what is the good initial value, so it could be anything. Then you say compute the gradient of f with respect to w, right? So which is just a vector of all the partial derivatives. Then you update W plus, so this is the key part. So here what you're doing is you're updating W using the derivative, right? So remember, W is a vector, this is also a vector, this is also a vector, this is a scalar value, right? This is what we call the learning rate. How much do you want to sort of increase by? So if you go back to our example of climbing Mount Everest, this is the step size, right? So I figured out that this is the direction in which I should go, but then I have to make a choice of I take a big step or a small step, and we will see how that matters, right? But this is also something that we specify. There is no easy way to find it in gradient descent, but there are other algorithms which sort of do things in a much smarter way. Okay, if you're now, this is for maximization, if you're trying to find the maximum value, but if you're trying to find the minimum value, then this becomes negative. Okay, for minimization, the update step changes. For minimization, update step is minus, because you have to go down, right? But everything else stays the same, right? So as long as you can compute your gradient, if you can compute the gradient, that's all you need, and then you sort of tumble down or climb up. Yeah, any questions so far? So now let's see how we do this in the context of perceptron algorithm, because this is a general it's a general scheme, right? But the magic is in what is f and what is the gradient, right? So different algorithms will have different f. So today we'll look at the f, which is the objective function for perceptron. Next class we'll look at it for neural networks, and in your assignment, that's what you have to do, right? You have to compute the f for neural networks. Okay, so let me switch back to this slide, right? So this is basically our f. Instead of f, I've written e because it also tells you the error, right? So for a given weight, this is the error that we are trying to optimize. This is also known as the error of the unthresholded perceptron. I talked about all of this. Right, so this is the general gradient descent, right? Gradient descent is always, of course, descent. I should not call it maximization, I'm sorry. So gradient descent means that you are sort of always going to go in the negative direction. If you're trying to find the maxima, we should call it gradient ascent, which is just flipping the sign. So no problem. So you can think of this also as updating each component in your weight vector using the partial derivative, right? So it's the same thing. Okay, any questions so far? All right, so let me now the question is, how do we compute the derivative or the gradient of the objective function for perceptrons, right? Because that's basically, that is how we come up with new machine learning algorithms, right? We define a new objective function, and then we compute it, we try to maximize it using some method. Okay, so let's see. And what I'm going to talk about right now is also in the handout. So if you don't follow everything, you can refer to that, but do ask questions if you have right away. Okay, so here it is. Let's see, put the date A43. Okay, so remember our function, our objective function that we know called E of W is nothing but 1/2 summation yi minus W transpose xi square. So let's say we have n training data examples, right? So all we are doing is we are trying to compute the total loss. So this is how much error you have from your, so this is what you want, this is what your system gives, right? Your algorithm gives, so this is the error. So now we need to compute the, oh actually not this, we need to compute the gradient of your function, right? So there are two ways to do that. We can straight away jump into vector calculus, and it's easy to do that as well, but let's try to do it one at a time. So let's compute the partial derivative of E with respect to W, some weight entry Wj, because they're all unknown, right? So this would be, I'm going to go fast, assuming that you follow, but if you don't, please raise your hand. W transpose xi, right? So xi is a vector. It's a vector of d attributes. W is also a vector, right? So now if you do that, what you do is derivatives will go inside the summation, and inside the summation the derivative of this will be summation I equal to 1 through n half 2 times yi minus W transpose xi, and then the derivative of this respect to wj. Now remember, this is constant, right? So it will be 0 minus, and now let's look at this quantity. We have to compute d by d, right? And this is all into the summation. We'll cancel this 2 out, right? Now remember, what is this? This is the inner product between the weight vector and xi. So you can write this as a summation over j equal to 1 through d wj xij, right? That's the dot product. Now when you compute the partial derivative of this whole summation with respect to wj, rest of the terms will go away because they do not depend on wj. Only the, well, I should use some other thing, k equal to 1, k equal to 1, k I k, right? So only the jth entry will matter, right? So this can be written as yi minus W transpose xi and minus xij. So is that clear? That's pretty straightforward, right? They are just getting multiplied and you're getting the value. So this is the partial derivative. So now what you do is you can compute the gradient by just sticking everything into a vector. So you will say that for j equal to 1, this will be yi, this will always be the same for everything, and this will be minus xi1, and then so on, right? So that is a derivative or the gradient, and then you can compute your you can do your perceptron algorithm, right? Any questions so far? Fairly straightforward. Okay, so let me show that to you on some data just to get you a little bit of feeling about how this works. So if you go back, if you go back to our discussion from last class, I had this whole notebook, right? So one half of this notebook was about perceptrons when the data is separable. Your concept is in your hypothesis space. But the next part is about the non-separable. So let's go through that, okay? So let's first look at this. So I create some data just because we are doing a demo. So I create this data. Sorry. Where is it? Right, here it is. So I create data using some existing function that is there in the sklearn library. sklearn is a machine learning library in Python. I think later on we'll talk about it a little bit. But so there's a simple function that lets you generate some data. So let's say this is your data, okay? There are two colors, which means there are two classes, and the data is defined in two-dimensional space, okay? So what I have done is that I have written the perceptron algorithm here, okay? So we have set our learning rate to 0.01, and later we'll see how that affects the whole thing. And then I start my initial weight vector all once. Now we have to learn 3, right? Because we will have 2 weight vectors corresponding to these and 1 weight element corresponding to the bias term, right? So and you will see that I incorporate the bias, okay? So what I do is I run this is an iterative algorithm, right? You keep, because you have to keep making a step at every point and then you reach the top, right? And now when to stop also is an interesting question, and we'll talk about that as well. So first what I do, and this is just I'm computing. So I'm computing the loss. So if you go back up here, this is the loss function. So this is a loss function which is the E that I compute, right? So first what I do is I add a vector of 1s in the beginning. So that's to incorporate the bias, right? Then I compute my prediction. This is X transpose W, right? I am doing this for all of my training data in one go. So instead of having a summation, I just do the whole data matrix times W. It makes it faster. So that's another tip for all of you for your programming assignment, is that try to avoid for loops as much as you can. because for loops are very slow in Python. Try to use the function dot to do matrix multiplication, matrix vector multiplication, even vector multiplication, right? That'll be much faster. But anyway, and then I compute this loss, which I wrote earlier as well, right? So this is exactly what I talked about earlier. So I compute the loss, but what we really want is to compute the gradient. Grad equal to compute gradient. Now, if you look at compute gradient, it is exactly what I talked about earlier. It is the inner part multiplied by the jth entry. So you compute the partial derivative with respect to every entry in your weight vector, and that gives you your gradient, right? And then what you do is, then you just update your weight. You keep going along in the negative direction of your gradient, right? And at every point, I also plot things. So all of this part is actually not necessary for your gradient descent. So I can, if I delete this, I delete this. That's it. Gradient descent is just 2 lines. You compute the gradient, you update your weights. And of course, you need to initialize stuff. But I do this just because we want to see how things are changing, all right? So in general, gradient descent is pretty easy. One more thing you will need to do later on is try to figure out when to stop, right? Right now, I'm just running it for 20 iterations. But what you need to do is at every step, you need to check if you have converged. So every step, you need to see, am I changing at all anymore, right? So if I've reached the top, what will happen is that I might not get there might not be any direction to go into, and that's where you will converge, right? But right now, just for simplicity, I have just run it for a few iterations. So let's just run it, and then let's see what happens. I also compute the mistakes that we make, and this is an interesting discussion that I want to have later on. So this is my data, and clearly this is not linearly separable. And now I run it for 20 iterations. Let's see what happens. It's because of the plotting, it takes a little longer. But okay, so let's begin with this, right? So in the beginning, this is the line that we started with, right? It's not a very good line because this line, and then I also color things according to what class it is. So blue means that that's the blue class, and red means red class. So this is not a very good line, of course, right? Because it is putting a lot of red in blue and this and that. So that is not good. And then I also compute the loss and the fuss. It's actually just 1 point over here. So the loss is pretty high. And the number of mistakes you make, which means the number of points that you put in the wrong side, is 28, right? Pretty high. Then we take the next step. We update it W in direction of the gradient. And then you see the line moves a little bit. The loss goes down. It will go down because you're going in the direction of the descent. And the number of mistakes goes down as well. Then you keep changing it, the line keeps changing, and you keep sort of going down, 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 down. And at some point you will see that your loss will not change too much, right? Because of course this data is not linearly separable. So it will never, there will never be a situation where you'll have zero loss, or zero number of mistakes. But but it will still sort of keep adjusting it a little bit, and then yeah, so it keep going, right? So that is the idea. And then maybe at this point it says I'm done, right? Actually, technically, if you had done a little smarter convergence check, you might have stopped earlier itself. So which is the thing, right? So that is just how gradient descent works, right? Any questions so far? Oh yes. How do you design learning rates? It's a good question because that was my next point. But okay, yeah, we can do that. So let's look at what happens if I change the learning rate first, right? So let's say instead of 0.01, I make the learning rate 0.001. So now what you will see is that as the data progresses, the line will change very slowly, right? It's just going down really slow. So you might have to wait for a long time before it really comes the right answer, right? So very small learning rate is not good. But what if I make my learning rate too high? Maybe you might not see that here. But there are issues with making learning rate too high. If you make learning rate too high, you see here what happens. The error sort of goes up and down. It's just crazy, right? It's just jumping up and down. So you can think of this from our Mount Everest example, right? So if I'm trying to climb Mount Everest and I know I have to go in this direction, if I take very small steps at every point, it'll take me forever to reach at the top, right? But if I take very large steps, right? If let's say I was a giant and I was right before the top, but I took such a large step that I crossed over the top and went on the other side, right? So now, next step, what I'll do is, I'll again compute the gradient. It will be this direction. Now I'll take a step and then get this side, right? So I'll be dancing all night long, right? I'll become very fit, but I might not reach the top. So that is a problem. So the problem is that you cannot choose a very large step size and you cannot choose a very small step size. You choose the right step size, right? But the issue is that there is no good way of figuring out what the step size is. So there are a lot of variants of gradient descent. So the basic variant will assume that you know the good step size, so you'll set it. So maybe you can do some cross validation. You can look at these kind of plots and figure out, okay, what is a good step size. But then there are other algorithms. There's something called there are adaptive algorithms. What they do is that as your iterations increase, your step size, you start with larger step sizes and then you gradually sort of make them smaller, because you assume that as you reach the top, you don't want to take very large steps. So that could be another way, because that's a middle way. But then there are other methods, the second order methods, like the Newton's method, which we will not talk about, I guess, until we talk about logistic regression maybe. Newton's method, what that does is that instead of using a learning rate, it uses the second derivative to figure out how much to jump by, right? So the difference between Newton's method and the simple gradient descent is that the update is W becomes W minus H times gradient, okay? So instead of eta, which we need to specify, we use the Hessian, which is the second order derivative, to figure out how much to jump by. So these are a little more robust, but for our sort of understanding here, we'll assume that we know what a good learning rate is, and we'll do that, okay? Then there are other variants as well. So the whole numerical optimization is an area in itself, so I do not want to go into that in this course. So here we'll assume that, okay, we know what eta is, but with the understanding that if you do not choose eta wisely, you might either take too long to converge, or you might oscillate or not reach the right place at all. Okay, any questions? Good. All right, making good progress today. Okay, let me switch back here. So there's another step. So this is the general idea, and then there are questions like this, right? So convergence in the case of gradient descent is guaranteed if the data is convex. Oh, your function is convex, right? Which means that there is only one global minimum. So then it will reach there, but it will converge, right? If it is convex and your learning rate is small enough, then it will converge. And we saw what happens if learning rate is very large. Okay. But there are issues. It's not like a very good algorithm. It's not like we use that everywhere. So Google doesn't use it right away. I mean, just the basic version, right? Because it has issues like slow convergence. Because you would rather have small eta, because small eta means you will converge, but it will take longer. So you typically tend to be biased towards small etas. But if you keep small eta, then your convergence is slow, which becomes an issue in practical settings. Plus, you tend to get stuck in local minima. Okay, so there are other variants as well, and let me briefly talk about that. But before that, I want to talk about another thing. Right? Another question that you should be asking me is the question that why did we choose this as our error function, right? This is our error function, right? But we could have done something else as well, right? For example, what we could have done is we could have looked at the thresholded perceptron and tried to count the number of mistakes, right? Because because yi is always going to be +1 or -1, right? This value can be anything, and you're trying to minimize the error. But what you could have done was you could have actually tried to compute the number of mistakes you make, and then so that would be your error function. That would be your objective function, and you could have optimized W for that, minimizing the number of mistakes. However, that's not the reason why we don't do that is because those kind of functions will not be smooth and nice like this one. See, whenever you see a quadratic term over here, a square term, if you're doing numerical optimization, your heart becomes very happy because this kind of says that this is going to be a convex function. But if you're doing things like counting number of mistakes, then that function will not be a smooth function, right? Because number of mistakes will always be integers, right? So it'll be, maybe you make 5 mistakes, 6 mistakes, 7 mistakes, 8 mistakes. It will go, up and down like that. So that is not a very easy function to optimize. These are easier functions. Remember when we did the derivative of this, it was just like that, right? Because we compute that, we even added a half here so that the 2 that comes from there gets cancelled out and so on. But when this becomes a trickier function like number of mistakes, then it becomes harder to optimize, because ideally it is a number of mistakes that you want to optimize, right? Not this error. But we still do this because this is what we can do with known mathematical techniques. Minimizing the number of errors then becomes other issues. You want to look at integer programming and those kind of solutions for that. So for this course, we will always use these kind of errors. But keep that in mind, that the choice of the error function is also yours, right? It's not like you always have to use the squared loss. You could have used the cubic loss or loss to the power 500, right? And things would change. The reason we stick with squared loss is that mathematically it's easy to handle that, right? And it converges, and so it is nice and convex. So in fact, I want to go back here and go back to this situation. And if you look at, you can look at this, right? That was the reason I was displaying the number of mistakes, because if you look at the mistake curve and how it goes, it is a little more sort of abrupt, because it is counting the number, right? So it will always be a integer, and so it will have these weird weird changes or transition points. So it's very hard to optimize those kind of functions. So that is the reason we use these beautiful convex functions to optimize on. Okay, any questions so far? So one last okay, one last topic that I want to talk about before we leave is one more variant of gradient descent, which we call stochastic gradient descent, and that is something that is being used a lot these days, especially with all the deep learning methods. They tend to use stochastic gradient descent, and let me tell you why. So what stochastic the way stochastic gradient descent is different from gradient descent is that it looks at one training example at a time. Okay, so what that does is that okay, so stochastic gradient descent, stochastic, GD, and there's GD here, right? So remember, what GD does is, gradient descent, is that it does W is W minus eta times gradient, right? It turns out that stochastic also does the same. The only difference is what is it doing here, right? So in GD, the gradient is defined as of course, the partial derivative, right, of E. Of the E, right? And here also this is the the gradient of this function E. But E is different for both cases. Here E is summation over, it's a gradient descent, summation over all training examples that you have. Okay, so this is yi minus W transpose xi square, half of this. In the case of stochastic gradient descent, is you actually only look at one training example. So this is E will be just half of yi minus w transpose xi. So in this iteration, you're only looking at the ith example. So there are two loops in stochastic gradient descent. What you do is you have a bigger loop while not converged, okay, and then what you do is you say for I equal to 1 through n, if you have n training examples, right, and then what you do is you do kind of like GD, but assuming that your training data has only the ith example. So you say so you of course you do w is w naught, right, and then you say w is w minus eta times gradient of E, right, where E is just this half yi minus w transpose xi. So there is no summation, and then you keep doing that. Oh no, sorry, there is another loop here, right? Sorry. So there's a loop here while not converge. So you take the first training example and then you run essentially the gradient descent until it converges for that training example. Then you go back and look at the second training example and keep doing that. But in the second example, you use the weight vector that is coming from the first example and so on, right? So the reason this is good is that so there are some interesting properties of this stochastic gradient descent versus gradient descent, and we will not sort of go into why it is so. That's a little more detailed discussion that we might have, outside this course. But it is known that stochastic gradient descent tends to avoid local minima better than gradient descent. Okay, so in real world, the functions will never be like this, like purely convex, right? They might have small local saddle points in the middle, right? But we still apply gradient descent. But if we apply stochastic gradient descent, it has been shown that it tends to reach the global minima more often than gradient descent. Okay. Another good thing about stochastic gradient descent is that you can use it in an online setting. So let's say your data is not available to you as a batch, right? Instead, it is coming from a stream. So you first get the first training data point. You can do gradient descent on that, the stochastic gradient descent, and that becomes your weight vector so far. The next one comes and next one comes. So it is easier to use in online settings because you look at one training data point at a time. Okay, so in many practical environments, it's sort of easy to handle that way. Of course, and then every time you do not have to do the whole summation, right? Every time you just need to compute the error with respect to one training point, which means that it's computationally also it's a little less expensive. It's less expensive in each step because in each step, the error, the grade, when you compute the gradient, you do not have to do the summation over all data points, right? So that is sort of one difference. The reason we call it stochastic is because we are not assuming what order the data is coming in. So the data is coming to us through some random process, right? So that's why the stochastic term comes into. So which means that depending on the order, your solutions might be different, right? But typically, if you have enough data and you have a lot of data coming in, then it might not matter. But that is the reason there's a term stochastic there. But in the course, in the assignment 1 and 2, we will only look at gradient descent. We won't look at the stochastic version. Any questions so far? Okay, all right. So I guess, let's see, do I want to move on? I do want to just introduce to you what we are going to do on Monday. We are going to essentially make things more interesting. So instead of trying to learn lines, now we want to learn curves and so on. So that's where we'll start looking at neural networks.